everyone. In the previous videos, we have developed a formulation for buckling, and then we have also taken up an example. Now, what we are going to do in this video is consider an alternative formulation for buckling. Of course, our starting point is going to be the same. That is, we are going to start from the principle of virtual work. In fact, the point that we are going to begin with is one of the starting points which we had seen in the previous formulation itself. Now, the motivation for taking up this kind of an alternative formulation is to make some headway or motivate the discussion for our subsequent formulation, where we'll be trying to go towards a more exact theory for buckling. As we have seen earlier, there are certain problems when we consider the response diagram associated with the previous buckling formulation. So we'd like to make an improvement on that. Towards that end, let us first take up this alternative formulation, and it is this alternative formulation which is going to motivate our subsequent discussions. All right, it will also give a nice insight into the various terms that were involved previously. Okay, so in this alternative formulation, what we are going to do is we are going to set this particular term that we had, du as dx, that equal to minus half dw dx square. Okay, now this may seem like absolutely out of the blue. Of course, none of this is going to make sense if you have not watched the previous videos, so I strongly advise you to do that, the buckling formulations and as well as the example. But even if you have done that, even if you have watched those videos, setting this kind of a thing may seem absolutely out of the blue. So what is exactly going on here? So what this basically represents is the shortening of the beam, okay, as a result of the buckling. Now, at this point, I am not going to justify that kind of shortening. Rather, what I will do is utilize this this particular expression, see what it gives me. Okay, because if it doesn't give me anything useful, then I mean, there's no point in justifying it. Okay, so let me first try to show you the result of using this, and then I'm going to justify it. Okay, so it will represent the shortening of the beam, but I'll take that up later. So what I'll just write is that to be justified later in this video itself. Okay, so the point that we're going to start off from our previous formulation is this step. Okay, one of the first starting points, not the exact first starting point of where we started using the principle of virtual work, rather one of the subsequent steps, but still very early on in the formulation. So I strongly encourage you to take a look back at that formulation to see where exactly this particular equation turns up. So that's my left hand side obtained from the principle of virtual work, and then on the right hand side I have this. So if you remember from the previous videos, we had utilized or we had developed our formulation by considering the left hand side and the right hand side separately. This is what I have done here is basically consider them together. Now this EXX, this nonlinear strain, that this expression was du s dx minus z d square w dx square plus half dw dx square. Now, because I'm going to utilize this particular expression, it's my choice as of now, it's going to be justified in a while. What happens is that this expression of Ex, it gets really simplified to just this single term. Now if I use this back here, what happens? Let's see that. Again, I point out that this E represents the or denotes the Young's modulus. This B represents or denotes the width of the beam. Now just substituting it here, what I'm going to obtain is Z squared. So I'm again skipping a step ahead. All right. And what I'm going to do on the right hand side, so I'm going to play a little algebraic trick here, okay, or you can say a calculus trick here. In writing this term, which is like a boundary term, uh, in the form of an integration. So what I'll do is I will write it like, sorry about that. So you see what I have done here is to basically note that if I write it in this particular form, then you can almost see that this dx and this dx kind of cancels, although in a very strict mathematical sense, I mean, it's better not to think like that kind of canceling, but you get the understanding of what I'm doing here. So uh, what you'll be left with basically is this p delta d of delta us, and in the subsequent step you are going to obtain this term back here. Okay, so you can easily see how you can go from here to here. Okay, so it's kind of reverse engineering its source like this. Okay, now uh, this thing, this d squared w dx squared, this term again, these are independent of z. E and b are constants, so these can be taken out of the integration with respect to z, and what remains is this integration minus h by 2 to h by 2 z squared dz. So b together with that integration with respect to z is just the second moment of area. So what I'll obtain here is this ei d squared w dx squared and d squared delta w dx squared dx. On the right hand side, this d delta us dx, uh, that uh, can be uh, substituted, or this can be written using this. Okay, so what I'll do is I'll basically take the first variation of this expression. So what I'll end up with is integration 0 to L. This minus goes away because on this right hand side I also have a minus, and the speed remains of course, and then I have a dw dx and then a d delta w dx. Okay, so next what we are going to do is basically carry out our familiar steps involving the integration by parts, and then to see what really happens, what we obtain from there. Okay, so after integration by parts once, I have this term, I will, in one step, carry out the integration by parts twice in order to reduce this uh, term involving the second order derivative to a term involving no derivative. Okay, we have done this step quite a few times earlier, so I'm skipping ahead and doing it at one shot. I get a plus here because this is the result of the second integration by parts. Uh, so that takes care of my left hand side, and on the right hand side I'll just have to carry out the integration by parts on this integration only once, because there is only the first order derivative with respect to x for this delta w. Okay. All right. So once I have that, uh, I can immediately write down my governing equations and boundary conditions. Okay. So the governing differential equation, that will be formed by considering all the integration terms. So what I have here is this thing involving the delta w, and on the right hand side I have this another integration term involving this delta w. So I'll take them together. I'll also consider the fact that ei is a constant. Okay, so what I have basically from this term is ei d4w dx4 plus, because you note that this entire term is going to go to the left hand side, I'm going to take the integration all at once. So what I end up with is this p d square w dx squared, where again I have utilized the fact that this p is independent of x. Okay, so this thing is going to be equal to q, because I have this term also involving the delta w. For the boundary conditions, what I'll have is at x equal to 0 and x equal to L, either, so I'm going to utilize these boundary terms to write down my first set of equations, either ei d square w dx square is equal to 0, or dw dx is specified. So if you have already watched the previous videos, you should have absolutely no problem in interpreting what is going on here. Okay, why I'm writing this as dw dx is specified, basically just because we have this first variation here. Okay. The other set of boundary conditions will be by considering the boundary terms involving the delta w. So what we are going to have is either ei d cube w dx x cube, basically taking the EI out of this first derivative with respect to x, and considering this term, please note that there is a minus here, together with this term, what I will have is the dw dx. So basically what I'm doing is considering this term, this entire term, together with this term on one side, and taking the coefficient of the delta w. Okay, so this is the coefficient of delta w, so that must be equal to 0, or w should be specified. We have seen through our example of the buckling problem in the previous video what is the significance and how these particular boundary conditions should be utilized. All right. Now, the key point to note here, like the whole point actually of doing this thing, is to illustrate that if we indeed start, as we have done in this slide here, if we indeed start with this thing, du as dx equal to this, then the final set of equations, the governing differential equation and the boundary conditions that we have obtained, these are basically the same set of equations that we had obtained earlier. Okay, so these are the same set of equations obtained earlier. So previously, in order to uh, arrive at these equations, we had to go through quite a tortuous route where we first found out two sets of governing differential equations, one involving the US, the other involving, or rather some kind of a coupling between the US and the W, and then through some clever tricks we were able to reduce it to one equation like this. So and then the boundary conditions also reduced to this. Uh, so what we have done by considering this particular thing, this particular expression, or setting this or using this equality, uh, for apparently no rhyme or reason, although I told you just through words that it represents some kind of shortening of the beam, we have managed to obtain the same set of equations. So it seems that there is a certain utility in using this equality, this du as dx equal to half is equal to minus half of dw dx a whole square. There is some utility in that expression. Okay, now comes the part where we have to justify, okay, why that is true. Otherwise it is all arbitrary. Okay, it may be just like an algebraic or a calculus accident that it just happens to be so. Okay, so what we are going to do is uh, go for some kind of a justification of why this thing works, and for that we are going to do this in this particular video itself. To make it self-contained, we are going to consider the geometry of the shortening of the beam. Okay, so justification for so it represents the shortening of the beam. Let's see why, I mean, why it represents that. All right, so what we'll do is we'll consider our our beam like this. Okay, and then let me make that better. So this is our straight beam now, and it is of course subjected to this these loads at the two ends, and as a result of that, what happens is that uh, this beam, it maybe that's a little bit too exaggerated. Let me just correct that. Okay, something like that. Try to make this a slightly better. Much easier to draw on the chalkboard. Okay, I think I'm happy with that. Uh, so what is happening is that when the buckling really occurs, then the shape of the beam, it becomes like this. At least uh, in the first mode of buckling, uh, it becomes like this. Like, of course, when I say first mode of buckling, you have to understand that immediately associated with that statement is the specificity of the boundary conditions and everything, but right now I'm not too much bothered about the boundary conditions. So you understand what is going on here, that there is a beam. As a result of the axial load, it is going to be bent out of shape like this. That is when we say that it has buckled. Now, as a result of that, the two endpoints of the beam, they have come nearer to each other compared to what was earlier. So if the total length is L, the the two ends, they have come nearer by a distance delta L. Okay, so when we say it represents the shortening of the beam, it doesn't really mean the actual physical shortening of the beam, rather the shortening in this sense. Okay, so, so just to make this thing clear, what we are going to say is that this particular distance, that is delta L. Okay, and suppose this entire distance, that is very much L. Also, you note that this distance, that is also L. Okay, all right. So uh, what we are going to do uh, is to first start out by trying to represent this delta L in the form of integrations. So you'll see at the end what is really going on here. So what I'll do is I'll write this in a slightly different fashion like this. Okay, it should be absolutely no problem to understand what I have done here. And then what I will do is I will write this L as, please note this carefully. Okay, there's some subtlety in what I'm going to write. Okay, so it's the same x here, but when I'm carrying out this integration, I'm going from here to this entire uh, distance in the undeformed or unbent configuration of the beam. But when I'm considering this integration, I am going from this endpoint to this endpoint. Okay, so I am considering this bent configuration, but I am moving along x. Okay, now this thing is better represented if instead of this x, we consider the a body fitted coordinate system. Okay, so, or a body fitted coordinate variable. So we use a body fitted coordinate variable s. So this s is along this. Okay, you understand that this s is along this. This is our s. Okay, so what I can write our delta L as 0 to L ds Also, this dx, so please note that that can be written as ds cos theta. Okay, so what is this theta? This theta is the angle that this uh, a tangent to this curve or this bent shape it makes with the horizontal. Okay, so it's like this, that uh, if this is our s and this is our x, so you are considering at a particular point, uh, this is our theta. All right. Uh, Now, where do we go with this? Uh, you see, uh, let us not lose sight of what we're trying to do here. What we're trying to do is to obtain a justification for this. So no matter what we do, our ultimate goal here is to arrive at this equality. Okay, so we are going to look at this delta L in two different forms. So right now what we have done is fine, and this will be of some consequence later on, but what we'll do for now is to go back for this integration at least to this dx. Okay, so let me go to the next slide. Delta L is equal to 0 to L ds minus, okay, now this ds, you please note, uh, it's something like this, that if I consider a little infinitesimal length of the bent beam, so this is my ds, this here is my dx, and this part, okay, this how much it has deflected, that will be given by dw. Right, so what I can do is to write this ds as dx squared plus dw squared, and that in turn can be written as 1 plus dw dx square root of that dx. So I'm going to use this here, 0 to L. Now I'll have to make a modification in the limits here because uh, because I'll just do it. Okay, so let me just complete it. So now you see this ds, it corresponds to this bent shape. Okay, if you go to the earlier slide, it corresponds to this bent shape. So when this s goes from 0 to L, our x, it goes not from 0 to L, because that 0 to L traversal of x, it represents the unbent configuration when the beam was straight. So because we are dealing with this bent configuration, okay, so in that bent configuration, when s goes from 0 to L, it corresponds to x going from 0 to L minus delta L. Okay, so that's an important point. So what we are going to do here is to write this as L minus delta L. Okay, the second integration, that remains as it is. Fine. Now what we are going to do here is uh, we'll take uh, an approximation of this in a series fashion. So instead of this equal to, what we are going to do is write this as approximately equal to, and then write this in this fashion. All right. So you can see what's going to be next. This is L minus delta L half dw dx whole square dx. Okay, because you see this 1 times dx integration 0 to L minus delta L, that cancels with this 0 to L minus delta L dx. Okay, so we are left with this. So it is as if we have obtained a part of what we are looking for. It is just now that the US term which we have to take care of. Okay, so let's see how we can do that. So again, we are going to write this delta L and carry out a little trick with it. So what we are going to do is this. We are going to write this delta L not in terms of the dx or the ds anymore. Rather, we are going to write this in terms of the displacement of in terms of the displacement variable US. Okay, so how can we do that? Now you see this delta L, it is the magnitude by which the two endpoints have come near. But if you consider this in terms of the displacement variable US, so if you go back to this previous diagram, you see this delta L represents the magnitude by which the two endpoints have come nearer. But in terms of the displacement variable US, you remember that US is pointing in this direction, and let's not forget. Okay, so in case you have any trouble, our x is like this. Okay, so our US is also pointing from left to right. So if our US is positive in that left to right direction, okay, so what is going to happen is that we can write this thing, this delta L, as 0 to minus delta L. Okay, 0 to minus delta L with a minus. Okay, because this integration from 0 to minus delta L, that is going to give me just a minus delta L, but then to adjust with the left hand side I need this minus. So this integration, it represents the shortening of the beam in terms of the displacement variable US. Okay, now this particular thing can again be written as the US dx dx, where this integration limit of x, it goes from 0 to L minus delta L. All right, so I mean there is not much not much more to it. We just have to the trick is actually in here. Okay, there's a little bit of an algebra trick here, but you're familiar with that because of what we have done earlier. But the real trick is to just interpret this magnitude of the two ends coming nearer in terms of this displacement variable US. Now, because we have obtained this expression for delta L, and earlier we had obtained this expression again for the delta L in terms of the dw dx square. So if we compare this with this, okay, so comparing hash 1 with hash 2, what we obtain is US dx, basically we are considering the integrand here and the integrand here because the integration is the same. It is with respect to x and the limits are the same. So that is equal to minus half dw dx square. Okay, so this was what we had to justify and we have justified it. Okay, so hence justified. Okay, and this entire justification is based on the fact that we are dealing with the shortening of the beam. So this is what is basically capturing that and that shortening of the beam. Okay, and this is the whole basis for this alternative formulation. So going ahead, we'll see how this alternative formulation and this insight into the shortening of the beam will help us to formulate a theory which will be more exact compared to the previous buckling theory that we have developed. On that note, I'll end this video. Thank you very much.